Okay, so am I audible?
Yes, ma'am.
Okay, so for today's week, we will just do a summary of week 8. So, week 8 has a lot of um concept on some advanced things in Fourier series. So, in week 7 means last week live sessions, you must be familiar with Fourier series, right?
Yes, ma'am.
Okay. So Fourier series, you must also have solved some questions on Fourier series. So in today's session, we will take some more uh, complex topics on Fourier series. So I hope you must have watched some of the lectures of week 8 or uh, mm, no lecture has been watched for week 8 for now.
Ma'am, I haven't watched any lecture.
Okay, you have not watched. And what about Diksha? Have you watched some of the lectures of week 8?
Ma'am, only two lectures.
Okay, initial first two.
Yeah, yes, ma'am.
Okay, then I can take means all the lectures, proofs, and derivations in detail today, so that means one after doing this live session, once you watch those lectures, it will not take much of time. So most of the concepts I will clear today, some derivations and proofs of all this. So I will try to cover all the lectures like brief. If time permits, or if time exceeds, then I will try to cover the rest of the topics in the next session on Saturday.
Okay, ma'am.
Okay, so let's start. I'll just share my screen. Okay, let me start the recording first. Okay, so is my screen visible?
Yes, ma'am.
Okay, okay, okay. So let's start. So I guess most of you must have not gone through all the lectures of week 8. So I will start very slow with week 8. And since it's a little, yeah, so that's what I guess. So let me take it like step by step and try to just sum up all the things given in week 8 in detail. so that if once you watch those lecture, it will be easier for you to navigate through those lectures. Okay, so in the first lecture, the convolution of two signals uh, is no, not the convolution, the multiplication of two signals. Okay, so you know that zt, if suppose is one signal that is in time domain, it can be written as a Fourier series. Okay, it can be written as a Fourier series. And what will be that? It will be like summation minus infinity to infinity ak e to the power j k omega t. So this, like, now after taking the week 7 sessions, this is pretty much clear. Okay, zt can be written as a uh, combination of Fourier coefficients and complex phasor with summation of all those k from minus infinity to infinity. Fine. So if suppose this is one of the signal and the other signal is suppose your vt, so again it will be written in some Fourier series minus infinity to infinity. So let's name this coefficient. So this k is varying. Okay, so k is varying from minus infinity to infinity. Here let's take some other symbol, say n equals to minus infinity to infinity, and it's going from bn e to the power j n omega t. Clear? So now if some question is there where you have to find the uh, some signal, say wt, which is equal to zt into vt. Okay, so this is one function and this is one function. You have to find the product of these two functions. Okay, so what the property of this Fourier series says? This says that this has the coefficient ak and this has the coefficient bn. So the coefficient of this omega t. Okay, so product, first of all, product of two Fourier series gives a Fourier series. So this can also be expressed. So this is what zt into vt. Now again, so when this is Fourier series, so this will again have that phasor and Fourier coefficient form. So suppose m equals to minus infinity to infinity cm e to the power j m omega t. So what needs to be done, rather than calculating like whole all the steps, what the property says, this we need to only calculate this cm, which is nothing but convolution of ak convolved with b of n. Okay, so the property says this. So if some two time domain functions are there and they are multiplied together, then the coefficients of those uh, Fourier series are convolved together and vice versa. If zt convolved with vt, then ak into bn will be the case. Okay, so your cm will be what? It will be k equals to, okay, and so what will be this cm? So how many this will have? So m is nothing but k plus n. Okay, now let's try to prove this property. Okay, you can use this property directly in your question, but let's see how is this coming. So your wt, I'm going to write it as zt into vt. So zt is nothing but infinity to infinity Okay, I'm sorry. So there was some disconnection from my tablet. So just let me know where I lost you. So I'm just sharing my screen again. So now is my screen visible?
Yes, ma'am.
Okay, so where did you lose me? Means so this Parseval's theorem. Did you like? Did I cover?
No, ma'am.
Oh my god! And this thing, like the convolution,
And you were on the second line, I guess, in this.
still here?
Yes, ma'am.
Still.
You were just writing that you just wrote that sigma.
Oh god. Okay, so whenever I get lost my connection, no, just ping me in the message. Okay, in the chat box you can write, because and my speaker is on in the tablet but not in the laptop because it will echo. So just let me know. Okay, so I will just start again. Yeah. So zt multiplied with vt. So now uh this is your, okay, so I've expanded it, nothing. So in this part, I've just expanded it. Okay. So once I've expanded it, I have written it through that distributed and associative property. I can write it like this. Okay. And AKBN, so this is nothing but just the rearrangement of this first line. So from here, we can say that if this part, so this part can be written as CM, and then this thing is written here like this. So this is again a complex phasor, and this CM is written like this. So this is nothing but AK convolved with your BN, means coefficient of Fourier series from first signal is being convolved with the coefficient of Fourier series of the second signal. So, if you remember from your earlier classes, the convolution can be written as like x tau ht minus tau, like integration. So, when we do it for the discrete thing, like Fourier series, we are doing the uh, discrete operation. So, this integration is changed to what? Summation. So, again, k equals to minus infinity to infinity. So, this is basically n. So, n is nothing but m minus k, because k plus n forms your m. So, this. So, whenever you have like two signals, suppose A, I will not write AT, like VT and UT, and you know the Fourier series for the same. Suppose this is some sine signal and this is some cos signal. You just have to calculate this. K equals to minus infinity to infinity. You just have to calculate this, and you will multiply them, just add them, and you will get the coefficients for your multi product of this, the signal which is the product of these two signals. We will get that. So this is the basic property which is being exploited when two signals are multiplied. Okay. So in this property, like the first one, convolution of coefficients of two signals when the signals are being multiplied in that time domain. Any confusion here?
No, ma'am.
Okay. So we'll take questions for this also, but it will covered in this on Saturday class. I will try to just cover up all the theorems and proofs for the Fourier series. So next property is the Parseval's theorem. So this is very important property. Like it should be like, you, if you have any doubt, just let me know. So Parseval's theorem says that if suppose there is some signal zt, okay, I'm taking zt. It's uniformly. I will take zt as an example. So, to calculate the energy of some signal in time domain, and which is what? Which is this. This is nothing but the area under squared magnitude of that signal. And you know this very well. Okay. But there comes a question. When you have a Fourier series like this, Fourier series for the same signal, does the energy remain same? Means if some signal is being expressed as your Fourier series coefficients multiplied with the complex phasor, then what happens to the energy? Is it sub scaled or something, or it remains the same? So what's your guess? Like, should it remain same, or should it differ, scaled, or something happens to the signal energy? Same.
Can you ask your question again?
I'm asking that energy of the ZT is suppose given by this, and this energy comes out to be, say, E1. Now, if I convert this ZT to its Fourier series like this, AK e to the power jk omega t, then if I calculate the energy of this Fourier series and I get this energy as E2, then tell me whether E1 will be equal to E2, or there is some relation that will be like E1 twice, or some E becomes half, or something happens to the signal, like multiplied with some coefficient. What will happen?
It will be equal.
Yes. So it will be equal. So let us see how. Okay. So now here, if you see this, so I have expressed some signal ZT in time domain, which is like a continuous signal. So when you take Fourier series of those that signal, no, so then what happens? You get the coefficients. This is nothing but you are basically calculating the components of frequency that is contributing to that phasor. Okay, that means you get it. So e to the power j k omega t. So your basically omega is nothing but your angular frequency, which is 2 pi by t, or you can say 2 pi f, and you get this k coefficient. So basically you will be able to get the frequency component on which that signal is operating. Clear? So from this figure zt, so let's take a very not very complex signal. Just take just taking a signal very simple, which is uh, suppose a rectangular signal. Okay, it's in time domain. So from this, only this figure, suppose it's going from -1 to 1. Can you guess only this figure? Can you guess the frequency components or the frequency of the signal? No, right? So So we convert into the Fourier series to get the particular coefficients, like a k value for different k's wherever that. So this tells that okay, this particular signal is having these frequency components, and this is like very 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 important aspect to analyze your signal. So to know your signal, which on which frequency it is operating. Okay. So Fourier series leverages it, means gives the idea of that thing. Okay. So now you know that the energy of your signal can be computed like this with integration. But Fourier series also helps to reduce this complexity. We will just see how it will help you in that. Okay. So so this is fine, right? So Fourier series, you get the frequency combos. So this is like, so in a way, what I was trying to tell is that this is just the representation, whether it's represented in time domain, whether it's represented in frequency domain. Frequency is just a Fourier series, you are converting to it frequency components. But uh, just the representation doesn't change the energy at all. Means you calculate the energy of this, you calculate the energy of this, it will remain same. You know how to calculate the energy for this. But if suppose you have something like this, you have ak, means for your coefficients for your signal, then how will you calculate the energy? Let's find out. Okay, so so this, if representing in Fourier series, so again k equals to minus infinity to infinity, and then you have your uh, ak e to the power jk omega t, and then so this is whole squared, the magnitude was squared, and then dt. Okay, because this part is nothing but your z of t. Clear? So now, easy t, how will we write this? We can take the summation out because the signal is orthogonal. So we can just do AK and then mag. So we're just breaking it. Okay. We are separating it out. So AK square e to the power jk omega t square, and then d of t. Okay, we get this. Now look very carefully, and okay, so sorry, I forgot this integration. Okay, so this part, mm, so now we can write it as equals to minus infinity to infinity, and then this can be taken out, so a k ka whole square, and then in the integration we are left with jk omega t square dt. So can you tell me the integration for this whole?
It would be, first we can write this as e j 2k omega t, and
Hmm.
after that the integration would be e j 2k omega t divided by j 2k omega.
Yes. So, so when you will solve this for a period of t, so this whole, so you can say it as one of the property that integration of your complex phasor gives a magnitude of 1. Okay, if it is not scaled. If it is scaled, then that not a, we can write some other variable like x. Okay, so but this will give you 1, and this is another proof. So if you are facing any doubt in this, I can just uh, scan that proof, like how is it coming to 1, and then just share it in G space. Okay, so this will come out to be 1, and then dt, which is integrated over t. That means ultimately it's going to be t, capital T. So now we can write that your energy zt is nothing but t multiplied with uh, summation k equals to minus infinity to infinity and a k mod square. Okay, so this is very simple, because this is very simple. How? If you have some signal z of t, and you can easily calculate the Fourier coefficients a k and e to the power j zt is to a k e to the power j k omega t, and you are easily find once you have found out those coefficients, right? A k, you just have to simply magnitude squared and the summation of all the coefficients multiplied with your t will simply give your energy. So we will solve some simple questions on this also, that will help you in getting those activity and all those graded assignment questions. So So the basically the property is energy for any Fourier series is time period. So this is nothing but the time period multiplied with summation of squared magnitude of those coefficients and the summation. So this we calculate, and don't forget to multiply it with time period. So most of the time what happens, you okay, you find you are you know this formula. Students calculate only this part, like summation of squared magnitude of all the coefficients, and then they leave it. They don't multiply it with the time period. So this is very important. Multiply it with the period of that signal. Okay, so this is another property which is called Parseval's theorem. But this is a property which is following the Parseval's theorem. But Parseval's theorem, what is that? That says that be it the signal in time domain or in the represented in the form of Fourier series, but the energy remains same. So the Parseval's theorem is this, and so by that we calculate that energy this. So we can say that T summation of like k equals to minus infinity to infinity a k squared magnitude is equal to your this sorry, that T zt squared magnitude dt. So now you know two things, right? To calculate your single energy. So you have to like make a strategy in your exams wherever you are, ki whether what will take lesser time. So you have the zt, integrating the squared magnitude of it will give your energy faster, or just finding out the coefficients, taking the squared magnitude summation and then multiplying it with the time period, will that give your energy faster? You can just means calculate it by any method, the energy should come same. Okay, and we will try to do this in the next session. Some question, we will calculate the energy by this method also and this method also, and we will see that whether the Parseval's theorem holds true or not. Okay, so this is, yes.
Ma'am, there's one question. I don't know where it was, but
Mhm.
it was on power, and
Oh yes, power. Huh. Okay, okay.
8K was
Yes.
given there, and
So,
it was
uh-huh.
not given anything else other than that. So
Yes.
I was not able to understand what the time period I should take, because less than k it was 0,
Hmm.
and greater than k it was always 1 by 1 plus k. So
Okay. First, like, you you put out this question, so I just remember to calculate the power as well. So thanks for pointing this out. But let me take your question. Like, I've not understood, but let me take that power thing. Okay. So now you know the energy of the signal. So power of zt. So you know that, and it's energy by time period, and you know here that it's t into your k equals to minus infinity to infinity squared a k squared, so divided by t. So the t and t will cancel, and you will only be left with minus infinity to infinity mod of a k and whole square. So here the time period is vanished, and you will be calculating the power like this. Okay. Now, yes, Ananya, you can go ahead with your question.
ma'am, I just checked and it was in graded week 7, so you can tell it in
Mhm.
next session, because week
Okay.
7 deadline is today.
Oh, it's is it still there? Week 7 deadline.
Yes, ma'am, it's today.
Okay, okay,
Yes,
okay.
ma'am.
Yeah.
Today is the deadline of week 7.
Okay, okay, okay. Though, so then I will take it on Saturday. Okay. Just make me remember about that question. So let me note it down. What's that question of? GA week 7 and question number?
12.
12. Okay, so we can discuss this first one Saturday. Okay, so the time period will just cut down, and we will only be left with this. Okay, so this part is clear.
Yes, ma'am.
Okay, so now let's move to convolution, but uh, in Fourier series. So what is that? So basically, what we are trying to do here is we are simplifying. So basically, main goal, the main idea behind Fourier series is simplifying of convolution. Simplifying convolution. Now, how is this achieved? Simplifying convolution. So, suppose we have some, so we are very good with this. Like if we have some signal zt and ht, and this is an lti system, and we get this output yt, so this is nothing but zt convolved with your h of t. Now, if some convolution is happening in time domain, then what will be that in the Fourier series? So this can be expressed as a separate Fourier series. This can be expressed as a separate Fourier series. So now, what will be the, like, your uh, convolution happening in your Fourier series? So let's try to find this out. Okay. So again, I will take the signal zt equals to k equals to minus infinity to infinity, and your ak e to the power j omega t. Okay, and where omega is your nothing but 2 pi by t. T is your time period of that signal. Now, okay, so now what will happen? So now you have another signal h of t. Okay, so just a minute. So now when we are convolving, okay, so then what is happening basically? Your x, your z is convolved with your h. So how we can write that signal? So suppose that is yt, that is z of t convolved with h of t. Okay, so your z of t, again we are expanding, k equals to minus infinity to infinity, k to the power j. So I missed k over here. Jk omega t and convolved with h of t. Okay. So how can we write this then? We can write this as, okay. So this is convolution, right? So convolution, how do we do that? Minus infinity to infinity. So we can write this as,
AK E J K omega
yes,
T
yes,
H
yes,
tau
yes.
minus
So
T
we will,
or T minus tau.
yeah. So e to the power j k omega t minus tau and h of, we can write this as t tau. Okay, so then what will happen? It will become, so y of t is equal to minus infinity to infinity summation ak, and then uh, so we will take one lambda k omega e to the power j k omega t. So here what is happening is your e to the power j k omega t is fine, that came with that vt. Okay, so here it's just the multiplication of ak and lambda k omega. But what is lambda k omega? So from the equation, the lambda k omega is nothing but integration of h tau e to the power minus j omega tau t tau. Okay, so this is the multiplication. So we are basically that ak is being multiplied with this, and your phasor, your complex phasor remains the same, and just we have to evaluate this, and this multiplied with your ak, which you already know for your zt signal, and you will get the output. Fine. So what is happening here is now it's a very critical point that we need to address is your your signal has some bandwidth. Okay, so your signal, suppose your signal is having some bandwidth. Bandwidth, are you familiar, like what is bandwidth?
A range of frequency.
Correct. So it's a range of frequency on which that particular signal is operating. So um this is a sinusoidal function. So this will only have one frequency, right? It will have some one peak. So that means the frequency spectrum of the sinusoidal signal is a an impulse signal giving the peak at the frequency on which this is operating. Okay, but there are some signals which is not just an impulse, but it can be a sync function. Okay, so means, okay, so now let us understand this. So if some signal is a rectangular signal like minus t by 2 to t by 2, that means it has a time period of t. So when you will do this in your Fourier series or frequency domain or your Fourier transform, you will always get a sync function. Okay, you are familiar with sync function, right? Sine pi t by pi t. So this is sync function. So now we can say that most of the information of the signal is here, like 3 dB band. So this can be considered as your bandwidth of the signal. So this is frequency. Make sure. So this, sorry, this is means your amplitude. This is your frequency. That means omega. Here it was t, and this is xt, but here this is x of omega. We write it correctly as j omega, and this is your omega. So this is your bandwidth. Okay, so bandwidth of this signal has been obtained by what tool? Frequency domain conversion, that is Fourier series. So bandwidth is rightly said by Ananya is the range of frequencies. So this is your range of frequency. Suppose this is corresponding to minus 2 hertz, and this is corresponding to your 2 hertz. No. So, okay, so here I've just put T. Okay. 2 hertz. That means your bandwidth is equals to 4 hertz. Okay. And one more relation, bandwidth is nothing but 1 by time period. Like the frequency. Okay, so is inversely proportional to your time period. Okay, so your signal has some bandwidth. Now, when you are convolving it, means you are passing it to some system, some LTI system, which has a impulse response HT. So your YT, what will be YT will have a bandwidth k omega from that Fourier series. Now this will always be less than your bandwidth. Okay, less than your bandwidth. How we can say that? Let's figure out. Now, instead of AK, we have two terms. AK lambda k omega. Okay, so now you can have some k where this lambda becomes 0. For some particular k value, this lambda becomes 0. That means ultimately your yt becomes 0. That means you have no frequency component over that k. But although your ak has some value on that k. Okay. So then the thing is, so this is your zt, and this has suppose four Fourier coefficients. Say minus 2, minus 1, 1 and 2. Okay, this is your k. Now you have your yt, which says that okay, ak remains the same. Ak is uh, this, but your lambda k omega has only satisfy only this minus 1 and say suppose 1. So this is for lambda k omega, the coefficients lambda k omega. Okay, so now you are multiplying. Okay, so yt is nothing but ak into lambda k omega. So altogether you will only be left with this frequency component and this frequency component. That means your range of frequency has decreased. Okay, so your bandwidth is decreased. It can also be equal, means if your k satisfy all the values for lambda, means there is no zero component for lambda for any of the k which corresponds to this k, then you have all the frequency components. But it can never be more than this. Okay, so bandwidth of your yt, that is the output signal, can never be greater than the bandwidth of your input signal. Is this clear?
No, actually. Can you explain that lambda part again? And also, are you saying that bandwidth is inversely proportional to 1 by t only because it is related to frequency?
Yes, that is frequency. Basically, this is frequency, nothing else. Okay, so that is like the relation is this. You can say it like if you have a bigger time period, means okay. So let's take this step by step, like all the things. So, firstly, about bandwidth. So, okay, you have one signal which is going from minus t by 2 to t by 2, and then you Fourier transform it, and in your frequency domain always a rectangular signal gives a sinc function. Okay, and the thickness of this main lobe, so this is your main lobe. Let's take the whole bandwidth. The thickness of this main lobe. Okay, so a time domain, that is t, and this is your z of t. When you convert this into Fourier, this becomes z omega. That means it's going to calculate this frequency components, and this is omega. So this is saying that for omega varying from this particular omega minus omega naught to omega naught, this gives your bandwidth. Okay, omega naught minus omega naught to omega naught gives your bandwidth of the signal. Bandwidth of the signal means range of frequency. So omega is nothing but the frequency. Okay. So from minus omega naught to omega naught, that means uh, your bandwidth is nothing but 2 omega, right? And your time period from here, time period of this signal minus t by 2 to t by 2 is t. Okay. Okay, so let's keep it simple. So I'm going from minus omega naught by 2 to omega naught by 2. So I get a bandwidth of omega naught. So omega naught is my total range of frequencies, which on which my frequency on which my this signal is propagating. From here, in this time domain, we were not able to see this, like how much frequency is it operating. Okay, so bandwidth is nothing but the range of frequencies it's covering. Okay, so this was your signal, and this is your. So I am saying that bandwidth is inversely proportional to your time period. This means what? So we have another signal, say, which has a greater time period, minus t, 2t, and now its Fourier series means Fourier transformed, and you get your omega, and then you get your, suppose, z2t and z2 omega. So I told that rectangular in frequency is a sinc function. Now can you tell me what change will happen to this sinc function? And you know this relation that bandwidth is inversely proportional to time period. Means if time period is more, bandwidth will be less. So then what will happen to the sync function? The same sync function.
It will decay to zero.
Not decay, but it will shrink like this. Okay, which means that this is your new bandwidth, which is going from, say, suppose, uh, minus omega. So earlier it was going to minus omega 2 to maybe minus omega 4 to omega by omega naught by 4. So since your time period of that signal is increased from minus t by 2 to t, your bandwidth will go down. Means the longer that duration of that signal till which it is on, the shorter the range of frequencies it will have, the lesser the bandwidth it will have. So because your time domain and is like analogous to each other, so if it takes more time, it will have less bandwidth. It If it is a short signal, like shorter time, it will have a bigger bandwidth. It will cover a bigger bandwidth. So, is this clear?
Yes, ma'am.
Because frequency is inversely proportional to time. Just that. This is the relation. That's fine. Okay. So, now coming to your, uh, huh, that this part now. Okay. So, now I am saying that now ZT, which we have just discussed, the ZT, when we convert into frequency domain, it suppose it has some bandwidth which we call at omega naught. So omega naught is the total bandwidth in hertz which that time domain signal is having. Now I have that YT signal, which is, so this is the input signal. Now I have that output signal YT, which is nothing but ZT convolved with ht, and which we have just seen that in Fourier series, which can be written as your k equals to minus infinity to infinity a k lambda k omega e to the power j k omega t. So, so this part you very well know. This comes from your CT. So when convolved with HT, it's just resulting in the multiplication of one another coefficient hk omega, which is nothing but minus infinity to infinity h tau. Um, what was that? E to the power minus j omega tau d tau. Okay, so I was mentioning that, so this yt, so the bandwidth of the output signal. So bandwidth of your yt will always be less than or equal to the bandwidth of your zt, which is the input signal. So bandwidth of your output can never be greater than the bandwidth of your input signal. And we will see how. Okay. So, so this is your K and this is your AK. And you have your frequency components, say suppose at minus 2, minus 1, K equals to minus 2, K equals to minus 1, K equals to 1, and K equals to 2. Now, your lambda k omega has the frequency components. So either it can have at all the frequency components that AK has, that is minus 2, minus 1, 1, 2, or it will be like it will not have it will have 0. Suppose it has at k equals to minus 2 and k equals to 2, the lambda k omega value is 0. So that means when you multiply this 0 with your AK, which is a non-zero value at minus 2. So at k equals to minus 2, your lambda k omega equals to 0, but your AK is not equals to 0. But ultimately, the product of these two means the coefficient for YT, you will get this as 0. Okay, so this can be one case. Or the other case where all the K, at all the K where the AK is non-zero, the lambda K is also not 0. So when the first case happens, means some of the components where AK is already present, but lambda K is resulting in 0, then your YT will have lesser frequency components, means your YT or Y omega will have a component at only minus 1 and 1, means your bandwidth range of frequencies has decreased from like if at 4 frequencies it was operating, so now it's operating at only 2 frequencies, means the bandwidth or the range of frequencies for the output has now been reduced. So this is what I am trying to tell. Like, so if your zt is going, so for the range of frequencies, like uh, say suppose this, okay, but your yt can only take so if it's going from minus t to t, sorry, so this is zt, but this is in frequency, so minus omega naught to omega naught. So you, so this is omega, this is omega. So now there can be two cases where initially the initially your frequencies are zero and it starts to have some components after some time, or you will have initially all of non-zero components and then you will have some zero components, or simply you will have the components at all omega. Okay, all range of frequency which the z omega has. Okay, so now so in any of the course have you studied like high pass filter, low pass filter?
Yes, ma'am.
uh, okay, fine. So now if I'm saying that earlier, so this is zero, this is omega, this is minus omega naught, this is zero, and this is again minus omega naught, and this is omega naught. So if suppose my input is this and I'm getting the output like initial from minus omega naught to zero, the components are not there, but from zero to omega, the components are there. So can you tell me which type of filter is it corresponding?
Ma'am, can you say it again? Question. Yeah.
Okay. So I'm saying that your z omega has this bandwidth, okay, minus omega to omega naught to omega naught means suppose minus omega naught is nothing but minus 4 hertz to 4 hertz. It's going like all the frequencies it's covering. So minus 4, minus 3, minus 2, minus 1 to 4 hertz. So I'm saying now your output, because output has the coefficient as ak multiplied with lambda k omega, and this results in your k absent at the initial till zero, so you don't have any components. So so minus 4 to 0 hertz there is no signal, but from 0 to 4 hertz you will get the signal. You can get it like this or like this, but your signal is there. So for the lower frequencies the signal is blocked, but for the higher frequencies the signal is passed. So what type of signal is this?
High pass
What type?
filter.
Correct. High pass filter. Okay, because here the lower frequencies are being blocked and your higher frequencies are getting passed. Now you passed it through some system which is giving your output as so your output from minus 4 to 0. Okay, it's passing till your lower frequencies, but as soon as it get the higher frequencies till 4 hertz, it's blocking those signals. So which type of filter is this?
Low pass filter.
Low pass filter. Get that? So the thing is, you can have, and this is like no filter because none of the frequencies is being blocked. So you have no such filter over here. Okay,
Ma'am, also we can say that it will be band pass filter because it is letting pass through a range of frequencies.
range of frequencies. Yes, we can say that. Yeah. So it passes through a range of frequencies. But comparing it with the input, if it's like, so if your input signal is like minus 4 to 400, it's covering all the signals, then there is like no frequency is getting blocked. But if some of the part is getting passed, like say suppose minus 2 hertz to 2 hertz, then you are selecting a range of frequencies from which the signal is passing, and now you can say that this is a band pass filter. Okay, so now let's try to understand in terms of LTI system. Okay, so in LTI system, if suppose I have again the input signal and it's passed through I say a differentiator. Differentiator. Then what will happen to this z of omega? So you will later learn once you convert. So this is different difference like d of dt. So this operator is applied on your z, the input signal. Your this Fourier series. So zt has this Fourier series. It will get multiplied with j omega. Okay. So in a way, so this is your LTI system, which is doing this differentiation, and your YT. So YT will be nothing but Z omega multiplied with J omega. Okay. So that means for whichever omega the Z omega was present, it's again getting multiplied with omega. So that means like, so if it was like earlier, this omega was some z omega was present here. Now it's multiplied and getting shifted to some higher signals, and the resultant will be some like this type of signal. So that means your all the lower frequency for which the z omega was present now it's zero, and it's accelerated or escalated to some higher frequencies as your output. So we can say that if you fit a differentiator as your in your system, you the output of that system will result in a high pass filter. So this is like the practical one. The ideal one will should look like this. Okay, and this is nothing but your high pass filter that we just discussed. Similarly, very analogous to that, when you pass it through an integrator. Okay, so integrator, so you have z omega divided by j of omega. Okay, so that means for the frequencies where the z omega is present, now it's getting reduced by some factor. That means your we have some lower frequencies at which the now my yt is there, but not for the higher frequencies. Again, this is a low pass filter. Okay, so so that means differentiator is giving a high pass filter, and integrator results in a low pass filter. So this is like the practical LTI system application, and you have seen from Fourier series, which gives the idea of frequency. Now you are able to know that you can build a your high pass filter or low pass filter. Okay, so this is for the LTI system. Now, uh, so we have some. Okay, we have some Dirichlet's condition. So where from which this arises? Dirichlet conditions. Now we are repeatedly saying that for a particular time period, if there exists a Fourier series for a signal zt. Okay, so this is again okay, and what about jk omega t. We are repeatedly saying that okay, we will get some Fourier series, we will get some Fourier series. That means your time domain signal zt converges to this function which is in Fourier series. But let me ask you, is it always true whether all the signals, any type of zt will give the Fourier series in this form? Is it true?
No.
Okay, so yes. So it is not true for all the signals. Okay, it is true for uh, like some of the conditions. If and only if those conditions are being followed, then only we can say that this is being converged with this, or there is a Fourier series possible for that zt function. Now, what are those conditions? So always the zt, when we are calculating in the Fourier series, we are calculating for a particular time period, and that is a finite time period. Time period, and that is t. And what is this t? How is it related with omega? So omega is nothing but 2 pi by t. Okay, so angular frequency for that particular time period. Okay, so now what is the first condition to have the Fourier series for some signal z of t? So that signal zt must be integrable. Okay, so integrable over that time period t. So that means your time period t, for that time period t, if you try to take the magnitude of this zt dt, it should be less than infinity. Fine. Means that signal should be uh, a finite signal over that given time period to have this Fourier series to happen. Right? It's very clear, because if this will be infinity, you will not be able to find out the k values for that particular series. Okay. So, uh, okay.
Ma'am,
Now
I
let
have a
me.
question.
Yes. Yes.
Why we are only writing T? What's the upper limit?
Upper limit as in means not getting like what?
When we are making that integration sign, we are writing the
Mm-hmm.
lower limit as T, but we are
Oh,
not writing
okay.
any upper limit.
Okay, okay. So the this representation, no, this. So this is not representing the integrating over this lower limit. This is just telling that we are integrating this within a certain time period. Okay, so that time period t, that is corresponding to that time. So this whole integration. So this is my signal. Okay, this is one periodic signal, and this periodic signal has a period t. Okay, so I am integrating the signal over this period t. So integration over a period t means we will only integrate the signal in this period, because each period will have the similar signal, right? So this is the representation for that. This is not the lower limit.
Okay, ma'am, got
Uh,
it.
Fine. Yeah. So this is a representation which we also use in that when we calculate the power of some signal. Always a power is being calculated like for a periodic signal over a period. So that period is t. So it's integrated over that time period t. So this is the notation for that. Okay. So now, so this is the very foremost condition. Like it should be integrable over that period. So now let me ask you one question. So I have a signal like this. Can you tell me what signal is this?
10.
Yes. It's a time. So now it's okay. So this is my like time period t. So now tell me for this time period t, whether the signal is whether the signal is integrable, whether it's like less than
No.
infinity. Yes. Okay. Now take another signal. I will draw just the impulse train of pulses. So these are the rectangular pulses. So now I am taking this time period as t. So now is this finite? The magnitude of the signal is it finite?
Yes, ma'am.
Correct. So the first and foremost condition is that your signal magnitude of your signal is finite. Okay, now the condition 2, it should have only a finite number of maxima and minima. Okay, so what is like maxima and minima? So your signal, suppose, so suppose your signal is oscillating like this, and again it starts from here, and again it's oscillating like this. Okay, so the signal has some maximum component and some minimum component, right? It has this and it has max and min. But those max and min should be finite. Okay, it should not be infinite, like continuously, like all there are many means at very small instantaneous time the maxima and minima are there, then the Fourier series will not be possible. Okay, the other thing is finite maxima. So you know how to calculate maxima and minima, right? So maxima and minima, where your the derivative of that function is should be equals to 0. So we calculate the maxima and minima, and those should be the finite values. Okay. Now your third condition is that it should have a finite number of discontinuities. Now let us understand what are the discontinuities. So again, I'm taking the same example. Okay, so now this is so at what, so do you find some discontinuity in the signal?
Yes, ma'am.
Yes. So
Here it is going 0 to 1 directly. There we have
exactly,
discriminity.
exactly. Yes. So add, if suppose I say this is the one. So here the discontinuity is happening at 1. Okay, it's immediately going. So suppose the value is 1 over here, it's immediately going from 0 to 1 at 1. So at 1 you don't know whether to take 0 or you take. So I will answer this question in the next uh, postulate, but you don't know whether to take 0 or you take 1. Okay, so this is the uh, discontinuity you are facing at whether to take 0 or 1, whether to take 0 or 1. But this is repeated. Okay, so at here also you don't know whether to take 0 or 1. So finite number of discontinuity doesn't mean that so it's periodic. So each and every pulse or rectangular function will have this discontinuity, but the discontinuity value will lie either 0 or 1 for each pulse. Okay, so in a particular time period there is only one discontinuity. Now let me take another example, like um okay, so this is one time period, and again, so in this example, the second example, we can clearly see that there are number of discontinuities within one time period. So for this case also, the Fourier series does not converge to this, means you cannot find the coefficients. Fine. Now the fourth one. Now fourth one gives answer for this type of discontinuity. Now you have, so this is like not possible. The Fourier series is not possible. So let's get back to where the Fourier series is possible. So, so for this, we have a discontinuity. Fine. So now, Fourier series at the point of discontinuity. Okay, so now if you get this Fourier series and you want to calculate the value of AK at K, so will it be 0 or will it be 1? It will neither be 0, neither be 1, but it will be the mean of left and right limits. That means average of 0 plus 1 divided by 2 means half. Okay, so the value will be K will be half. Okay, so this is your fourth, you can say, that Fs converges to mean of right limit and left limit at point of discontinuity. At point of discontinuity. Fine. So this is the uh, conditions which if are followed or are satisfied by some signal zt, then only the Fourier series is possible. Okay, fine. So is this clear?
Yes, ma'am.
Okay, so now let me end this lecture at this point. So for on in Saturday's lecture, um so there is one more thing, like, okay, so in next lecture I will be giving some examples to calculate the Fourier series of some very common input signals, that is your sine omega t, sine omega t, your, or just sine t, cos t, and your delta t minus nt. So delta t minus nt, are you getting? This is like a impulse train. Okay, and we will also see when this impulse train, okay, if it is convolved with some signal zt, then what will happen? So this will also result in some very significant sampling theorem. So this is the points that we will discuss. We will also discuss taking some example to prove the Parseval's theorem, and I can also take the doubts for your graded assignment of week 7. Okay, and also, okay, so that is also very new for you, your lambda k omega, right? So I will also take questions for uh, convolution in Fourier series. Okay, I will try to solve some questions on this as well. So these parts will be covered on Saturday. Okay, I hope I will cover it in 1 hour. If time exceeds, we'll see what to do. Okay, so now I'm just ending this lecture at this point. So, any doubts for today's session, what we have discussed so far? Gordon is not happening. Okay, okay. So then, okay, now we can leave. We will meet on Saturday. Thank you all.
Thank you, ma'am.
Thank you, ma'am.
Thank you.